Hello everyone, this is lecture number 2 for the module 6 for the computer organization and architecture course. So, in this lecture I am going to talk about the third IO technique, which is called as a direct memory access or DMA. So, I will discuss about how DMA works, how it is different from the other two techniques, IO techniques, that is interrupt driven IO and the programmed IO, and the various DMA configurations I am going to discuss in this lecture. So, first, before going to discuss about the DMA or direct memory access, what exactly it is, first we look at what are the drawbacks of interrupt driven IO technique and the programmed IO technique. Two techniques has been discussed in the previous lecture. So, as we discussed in the previous lecture that for the programmed IO and the interrupt driven IO, one common thing is that in both the cases the CPU's active intervention is required. How CPU is participating in both the methods in any IO transfer is different, but active intervention is must. So, say for example, in case of interrupt driven IO, processor initiate the IO transfer, means giving command, and then device will take some time. During that time processor can do some other work, and once the device is ready with the data, then the processor can finish the data transfer. So, at one starting and the ending is to be done by the processor, participation is required. In programmed IO, anyway processor is completely engaged right from the beginning to the end of the data transfer. So, due to this, the transfer rate is limited by the speed with which the processor can test and service the device, and processor is tied up in managing an IO transfer. So, these are the 2 points which comes in terms of the drawback of both the techniques. Using programmed IO, processor can move more data at higher rate at the cost of doing nothing else, because processor is always, you can say that, with ready for the IO transfer, it is tied up with the IO transfer. So, whenever the device is ready, immediately it is ready to transfer, no extra wait is required. In case of interrupt driven IO, frees up the processor at the expense of IO transfer rate. In interrupt driven IO, processor is free once it is given the initial command to the IO device, and after that the processor can do some other work, and then the device will send a interrupt signal to indicate I am ready with the data. So, that is a compromise. Compromise in the sense processor is immediately cannot respond to that interrupt. It may possible that processor may respond to that interrupt after some time. So, due to this, in both the techniques there is a compromise is there. Can we remove this compromise and do better compared to these two techniques? So, that is the overall objective here. So, for that the DMA technique is used. DMA stands for the direct memory access. So, let us see how it works. So, this picture shows the DMA module. So, in the DMA module, what are the components are there? One data count register is there, then data register is there, address register is there, and the control logic is there. Now, the control logic for IO transfer is shifted from processor to this DMA. So, DMA now you can say the processors, this IO transfer work is delegated to another component, another electronic circuit component. Earlier means in the programmed IO and the interrupt driven IO, this control logic is with the processor. Now this control logic is with the DMA. So that is the one difference we can see. So how exactly this DMA activity starts? CPU tells the DMA controller for the either read or write operation. Then it supplies the device address. Device address is stored in the data register through the data lines, and it also provides the starting address of memory block for the data, the block of data which has to transfer. DMA is better for, or IO technique for using DMA is better for the large amount of data transfer. So starting address of the memory block for the data is in address register, through the address line it will get, and then amount of data to be transferred, that will be stored in the data count register. So there is 3 information, including the one control information that is called as a whether the operation is to be performed as a read operation or write operation on the IO device. Then remaining 3 information supplied by the processor. Once processor supplied this information, now processor is free. Now processor can do some other work and DMA controller does the transfer. Definitely DMA controller requires the bus for this transfer. So bus is a shared medium, so processor at that moment when the DMA is using the buses for the IO transfer, processor don't have access on that. So processor cannot access any bus at that moment. Then what other work processor can do? The work which can be finished without the accessing the bus or without accessing the memory. At that moment processor can't access the memory. So the DMA has to take the charge of the buses. So for that DMA request for the bus, then the bus is, once the bus is granted to the DMA by the processor through the DMA acknowledgement signal. Once it is received, this acknowledgement signal is high, means now DMA have the control over the bus and it can use the bus for the transfer. And once the DMA has done the complete IO transfer activity, then it initiate a signal, interrupt signal to the processor to indicate that the transfer has been complete. And the read and write control signal are used to indicate to the DMA that whether the operation is read or a write operation. This interrupt is different from whatever we have discussed, the interrupt driven IO. These interrupts simply indicate to the processor that the transfer, the data transfer, block of data transfer has been over. So once the DMA controller completes the transfer, then it sends the, indicates the finishing of the task with the help of this interrupt signal. So this is the DMA module, how it works and what are the components are there. So if we try to understand exactly what is happening, as I said earlier, the logic of IO transfer by default it is there in the processor. If you simply remove that logic from the processor to the IO to the some other controller, that is called as, here it is called as a DMA. Now DMA will do this activity, IO transfer activity. So that is the logic behind this. So now how DMA does the transfer? Because DMA require the bus for transfer. Anything has to be transferred from memory to IO device or IO device to memory, the DMA require the system bus, hold or control of the system bus, and for that in the DMA module the control signals are there. Through that it can acquire the bus or request the bus first essentially, and then the bus is granted by the processor and then it can use the bus and then finish the task. So what are the methods through that DMA can request the bus or can do this transfer? So one of the method is called as a cycle stealing. So cycle stealing, in the cycle stealing, the memory accesses by the processor and by the DMA controller are interwoven. Sometime memory access processor can do the memory access, at that moment DMA can't do, and a particular cycle DMA is using the cycle DMA doing the memory access, then at that moment processor cannot access the memory, because memory access is through the system bus. Memory means here the main memory. Now system bus, whoever has the control of the system bus, that can use that memory access can do, other cannot do the memory access. So in this, the DMA controller takes over bus for one cycle, that is why it is called as a cycle stealing. So for one cycle DMA will take the control and it transfer one word of the data, either side, memory to IO device or IO device to memory. There is no interrupt, means no contact switching. Processor, sometime bus control is with the processor for let us say one cycle, other cycle bus control is with the DMA. When the DMA is using the bus, processor is not using the bus or cannot use the bus, because both at the simultaneously trying to use the bus, then it will be a garbage. So in this case no contact switching is not required. That is something here the DMA activity is different from the interrupt driven IO. In interrupt driven IO it is the contact switching. Processor is moving or switching from one task to another task. One task that it was doing earlier, normal we can say is a processing, and then once the interrupt is initiated or generated by the device, then it will jump to the interrupt handler program. Here this contact switching is not required, so that overhead is not there. Then CPU suspended just before it accesses the bus. At what time processor or the CPU can take the bus? At what time CPU can or the DMA can take the bus? So DMA can take the bus just before CPU try to access the bus. So that is a stealing, because why it is called as a stealing? DMA is stealing one cycle from the processor, that processor was supposed to use that cycle, bus cycle. So in a complete instruction execution cycle, there are three places where processor try to access the memory or try to get the or try to use the bus. One is fetching before an operand, or fetching data, or at the time writing the result, final result of the instruction. So there are three places in the instruction cycle. Definitely this activity slow down the CPU, but not as much as CPU itself doing the transfer, because the cycles are stealed by the DMA. These cycles were supposed to be used by the processor, but this loss, it will definitely processor will slow down, but it will not be slow down as much is slow down in the programmed IO or in interrupt driven IO. So now we look at in the instruction processing cycle, where are the breakpoints from where the DMA can steal the cycle from the processor, and we will see the difference between the interrupt driven IO operation and the DMA operation. So here you can see this is the instruction cycle. Instruction cycle is a composition of various steps. First step is fetching the instruction, then second step is decoding the instruction, then fetching the operand, execute the instruction, finally store the result, and then after completion, here the one instruction is complete, and then in case of the interrupt driven, processor check whether is there any interrupt signal is enabled or not. If it is enabled, then it will process the interrupt first and then come to the next instruction, otherwise it will go to the next instruction execution. So this is the one place
where processor is going to get the control of bus and do the memory access. Fetching, for fetching instruction definitely it will fetch from the memory. Decoding the instruction also it will, sorry, decoding instruction it is not required, so that is why here it is not there. Fetching the operand before fetching, so this is the one point where the DMA can steal one cycle. This is one point here the DMA can steal the cycle, and this is the third point just before storing the result. For storing result also processor requires the bus control or requires the buses. So via bus it will store the result in the memory. So just before this cycle, so this is the third place where the DMA can steal one cycle from the processor. If the DMA steal the cycle, at that moment processor can't do the store result. Here it cannot fetch the operand, here it cannot fetch the instruction. So processor will momentarily stop, and once the DMA will finish this cycle, then next cycle will be available to the processor. So these are the 3 DMA breakpoints where the DMA can break the normal processing of the processor. In case of the interrupt driven IO, the breakpoint is after completion of the current instruction only. Interrupt cannot break in between the current instruction execution. So that is why let us say interrupt was initiated maybe at this moment, second at this decode instruction time. So it will finish cycle 1, processor cycle 1, 2, 3 cycles will go, or maybe multiple cycles also go, depends upon the number of operands has to be stored, number of operands has to be fetched, and then only that interrupt can be serviced. So that delay is there. So that is why it delays the overall IO transfer in case of the interrupt driven. But in case of the DMA, it can be done in a faster manner. So DMA is usually better for large amount of data transfer. So the second mode, so that is the one cycle stealing mode. One cycle from the instruction cycle it can take, and then it can use this cycle for the transfer. Another mode is a burst mode. In the burst mode, the DMA controller is given exclusive access to the main memory. Exclusive access to the main memory means by giving the control of the buses or system bus to transfer a block of data without any interruption. Complete block will be transferred, then only the processor will take the buses, or processor can use the bus for any memory transfer. So for this, most of the DMA controller incorporates a data buffer, storage buffer. So it reads a block of data using the burst mode from the main memory and store it in its buffer, and then it transferred to the desired IO device, whatever is there. So let us say 512 byte block of data is read from the memory into the buffer of the DMA, and then later it can be transferred to the IO device as per the IO device speed is there. So as I said, this for the block transfer it is very good. Why? Because in case of if this block transfer activity is done by the processor without using the DMA or with the help of the processor intervention, either it can be a programmed IO or it can be a interrupt driven IO. Definitely interrupt driven IO is better than the programmed IO. So let us take an example of interrupt driven IO of transferring a block of data. Processor initiate first, not wait for that device to be ready, it will go to the some other work. When the device is ready with the first set of data, interrupt the processor, processor will stop the current execution, jump to the interrupt handler program and do that, transfer that one set of data, maybe 1 word or maybe 2 word, depends upon the buffer size and the device speed. Then by the time the device is ready with the next set of data, processor again will jump to the normal execution and execute the instruction in the program. Once the device is ready with the next set of data, again it will interrupt and the processor will intervene again and do the transfer, complete the transfer of that next set of data. So let us say in this manner, if you say I have to transfer 512 bytes and each time device is ready with the 1 byte only, then how many times processor has to context switch? In each context switch some cycles will be wasted. So and this same block transfer can be done by the DMA in a single shot. Continuous some cycles it can use and finish the transfer. So that in that sense the block transfer is faster using DMA compared to the other IO techniques which are used. Let us see some DMA configurations, how the DMA can be configured. Configured means how it is attached to the IO devices or to the system bus. So, here you can see the first configuration where one single bus is there, that is detached, and a detached DMA controller is there. DMA controller is a separate DMA controller is there, that is also connected to the system bus. This is my system bus, processor, IO devices, memory, everything is connected. So, in this case, this kind of configuration, each transfer uses bus twice. Let us say something has to be transferred from memory to IO device. So, from first the DMA will take memory, from memory to DMA buffer it will go, and when DMA will give this data to IO device, then also it will use the bus once again. So, this bus will be occupied by the DMA twice. Now, occupied by the DMA twice means processor speed will be slow, speed will be processor, at that moment processor cannot get the bus control. So, you can say the processor or CPU is suspended twice. Twice suspension means it is a penalty. The second configuration is using the single bus and the DMA controller is integrated with the IO device. This DMA controller can be a separate as in the previous configuration, and in this configuration it can be integrated with the IO device as well. And one DMA controller can work for or can work for the more than one IO devices as well, like IO module. So, in this case we can see here the DMA is integrated with the IO, can support one or can support more than one devices. So, in this case each transfer, let us say some data has to be transferred from memory to IO. So, in each transfer, in case of the memory to IO, DMA will occupy the bus and the transfer will happen either in a cycle stealing mode or the burst mode. From DMA to IO transfer, there is no bus requirement. So, in this case CPU will be suspended only once, suspended from accessing the buses. So, this configuration is better in terms of the CPU suspension. Here CPU suspension is only once compared to the earlier configuration twice. Now, the third configuration is where we have the separate two buses, one is a system bus, one separate IO bus is there. Multiple buses architecture, we know that. So, in this case again DMA is detached with the IO devices, it is not integrated with the IO devices, but still the bus requirement for any DMA transfer is only once. So, CPU will be suspended only once. So, here you can see how it is happening. Separate IO bus is there, system bus, through the system bus your processor and memory is connected, is usually always connected, and the DMA is connected to the system bus and IO bus. So, at the time of transfer data from IO to DMA, no system bus access is required. So, the system bus can be used by the processor at that moment. So, no suspension of the CPU. CPU will be suspended only when the DMA will trying to transfer the data read from the IO device into the memory, or the vice versa, memory to DMA, then in that case it will require only once the bus has to be suspend, system bus, or the processor has to suspend and system bus access require only once, and at the time of transferring from DMA to IO it do not require any system bus. So, the CPU suspension is not there. So, less the CPU suspension is there means more the throughput will be there, CPU can do more activity, or whenever the CPU requires the buses it can use the buses. So, these three configuration we have seen. Now, we look at the one in DMA controller which is used which is developed by the Intel, and it is called as 8237A DMA controller. How this DMA controller works. So, here how the DMA activity will start. Suppose some data has to be read from memory. So, memory read. So, I can say memory to IO transfer is there, some IO device. Or that IO device is, in this case, let us say it is a disk. So, disk to memory data transfer, memory to disk data transfer is there, reading from the memory, putting into the disk. So, how this activity will start? The disk controller will request the DMA for this transfer. So, DMA request signal will go to this 8237 DMA chip, 8237A DMA chip, and then DMA will request the bus control by putting the HRQ. HRQ means hold request signal as a high to the processor. Processor will finish the current bus cycle, not necessarily the current instruction cycle. That is the difference between interrupt and the DMA activity. So, processor will finish only the current bus cycle, and after finishing the current bus cycle, it will give the enable the hold acknowledgement signal high, or it will put the hold acknowledgement signal on high. High means it is enabled. That indicates to the DMA that okay, now you can use the buses, or bus control is with you. Once getting this control, the DMA will acknowledge the device controller ready for the data transfer. During the complete data transfer, this HRQ hold request will be on high. That indicate to the processor, okay, currently I do not have any access to the buses are with the DMA. Otherwise, garbage is possible if the both were trying to access the buses simultaneously in the same cycle. After that, the memory read signal, in case of the memory, because memory read is there, and IO write signal will be enabled, and the data will be transferred. So, the first address of the block, let us say block transfer is there from the memory, the first address will appear on the address bus. DMA will put the first address on the address bus, and it will read the data from the memory and put into buffer, or directly it can transfer to the disk. And for after reading every word, the data count register is there in the DMA. The data count register is decremented every time by 1, and once the data count register reaches to the 0, means that complete transfer is over. Now, let us look at some exercises on the DMA activity or the DMA controller. So, the first exercise is, I am reading the question: processor and IO device connected to the main memory via a shared bus of width 1 word. Processor can execute 10⁶ instruction per second, 1 million instruction per second. An average instruction requires 5 machine cycles. 5 cycles it required to complete one instruction. Out of these, 3 of which used to the memory bus. Means memory access is there in the 3 cycles, and remaining 2 cycles no memory access. Memory read write requires 1 machine cycle. Processor is executing background programs that requires 95% of its instructions execution rate, but not any IO instruction. Only the background work, means maybe processing related, no IO activity is not there. Assuming a processor cycle equals 1 bus cycle, processor cycle and bus cycles are equal here, means the duration of the cycle of the processor and duration of the cycle of the bus both are equal. Assume IO device is to be used to transfer very large block of the data. Then, if the programmed IO is used and each word transfer requires the processor to execute 2 instructions. In the programmed IO, you know, it requires some instructions to do this, processor execute some instructions. So, for each word transfer 2 instructions are there. What is the maximum IO transfer rate? So, that is the first question. So, what is the amount of time available? 5% only, 95% it is doing. So, only 5% time is available for the IO activity. So, 5%, so out of 10⁶ total into 5%, 0.05, this will give me 50,000 instructions per second. IO instructions can be used or can be executed. because 95% of the time processor is doing the background program, and for 5% time the processor can execute the IO instructions. So at the rate of 10 power 6 instructions per second, how many instruction it can execute in the remaining 5% time? That is 50,000 instructions per second. Now 50,000 instructions per second it can execute for IO, and to transfer one word it requires 2 instructions. So the transfer rate will be what? 50,000 divided by 2, so it is 25,000 words per second. That is the IO transfer rate can be achieved through the programmed IO. Now you look at, in the same scenario, if the DMA is used, then how it will happen, and DMA let us say is using cycle stealing. So we have total 10 raised to the power 6 instructions. Now we have to calculate number of cycles that DMA can steal. How many cycles are available? So number of cycles available, 95% instruction is background is using, and these instruction 3 of which use the memory bus. So remaining 2 are not using. So from the 95%, 2 cycles it can steal, and the remaining 5%, all 5 cycles are available, because therefore IO activity. If you compute this, you will get 2.15 into 10 raised to the power 6. These many cycles are available. 2.15 into 10 raised to the power 6 cycles can be steal by the processor. Let us assume that DMA can get all these cycles. There is no cycle required for setting, accessing, setting the device or other any control related activity. That is assumption. Maybe some cycles are required definitely, but let us say here do not complicate much. So 2.15 into 10 raised to the power 6 cycles are required. Each cycle is one word it can transfer. So the transfer rate here achieved, that is a far high than whatever in the programmed IO it can be done. If all the cycles can be steal by the DMA, that is also an assumption. Now the second exercise. Second exercise says a DMA module transferring characters to the memory using cycle stealing from a device transmitting at 9600 bits per second. The processor is fetching instruction at a rate of 10 raised to the power instruction per second. Now the question is, by how much will the processor will be slowed down due to the DMA activity? In the last question we have not seen that how the processor will be slowed down by the cycle stealing process, but here we are trying to, in this question we are trying to compute that how much processor will be slowed down by stealing the cycles by the DMA. So let us try to solve this. The device is transmitting 9600 bits per second, and it is transferring characters to the memory. Let us say one character is 8 bits. One character equals to 8 bits. So the number of characters per second will be 9600 divided by 8. So it will be 1200 characters per second. 1200 characters per second is transferring that device. At a time one character will be transferred, 1 byte. Now processor is fetching, let us say here assumption is processor is only doing fetching the instructions only. Only one activity processor is doing, and that rate at which the processor is fetching, that is a 1 million instructions per second. Or you can say one instruction fetch time is 1 microsecond. Now to transfer one character how much time is required? 1 by 1200. That is giving me 833 point something. So I am assuming 833 microsecond. Some fraction value also will come, 0.33, and I am neglecting this value. So 833 microsecond time is required to transfer one character. So if the DMA is using the cycle stealing, means after every 833rd cycle, because 1 microsecond one instruction is executing, and that instruction, one instruction is fetching in 1 microsecond, and that cycle let us say is steal by the DMA. So, in that case every 833rd cycle is steal by the DMA, then what percentage will be there? So, 1 by 833 into 100. So, the percentage will be 0.12 percentage. The processor will be slowed down because these cycles will be used by the DMA. So, the processor activity will be suffered by 0.12%, and that you can say it is a negligible. So, that is why DMA transfer or the IO transfer with the help of the DMA or using the DMA is better compared to other activity. So, let me write the solution here. Solution is 0.12%. DMA will be or processor will be slowed down by the 0.12%. Now, let us look at some review questions that you can answer with this lecture. The first question is, in general DMA access to the main memory is given higher priority than the CPU access to the main memory. What is the reason behind this? Second question is, how cycle stealing for the DMA is different from context switching which is used in the interrupt driven IO. And the third question is, why DMA is better for large size data transfer compared to the interrupt driven IO. So, these are three questions I think you can, once you go through this lecture, definitely you will be able to answer. Now, let us look at what things we have discussed in this lecture. We talked about the limitation of the interrupt driven IO and programmed IO, then the DMA structure and the function. We talked about DMA, various DMA configurations, single bus, dual bus, DMA is detached or DMA is integrated with the IO device, and the few exercises. So, thank you very much. Have a nice day.